Hello again. Today we are going to review for the third of our 4 exams. This exam is going to cover chapters 25, 26, and 27. So the chapters on current and resistance, on DC circuits, and the introductory chapter to the subject of magnetism. So let's get started with chapter 25. So we introduced the subject of currents. Now, current is the rate of movement of charge per unit time, and it can be a small number of charges, it can be a large number of charges, but how much charge passing a point in a given interval of time tells you the current. So if you know the amount of charge passing through a point as a function of time, you take the derivative of that function, and that gives you the current. The unit of current is the ampere. So 1 ampere is equal to 1 coulomb per second. Ultimately, the ampere is what gets defined first, and all the other electrical and magnetic units and constants that we discuss follow from that. Current can be positive or negative. So a positive current is defined as coming out of the positive terminal and into the negative terminal. And it's a little bit misleading given that it's the electrons, the negatively charged electrons, that move from negative to positive in reality. So it's a little bit counterintuitive if you know what's going on at the atomic level. But keep that in mind, that a positive current is defined as flowing from the positive terminal to the negative terminal. Now, the speed of the electrons moving in a wire is equal to the current divided by the electron density, so the number of electrons that are free to move per unit volume, times E, the charge per electron, or the magnitude of the charge per electron, times A, the cross-sectional area. So in general, the number density is very, very high, so the drift speed is kind of small, actually. That typical drift speeds in a wire are on the order of 1/10 of a millimeter per second. So what you have is a very, very large number of electrons moving not all that quickly. Current can be measured using an instrument called an ammeter. The voltage across 2 points in a circuit can be measured using a voltmeter. Ammeters are typically connected in series, meaning that all the current flows through the ammeter. Voltmeters are typically connected in parallel. So you connect the voltage the voltmeter from one leg where you want to measure to you have the front leg and the back leg measuring the points in the circuit you want to measure the voltage across. And that's connected in parallel. So only a small fraction of the current gets siphoned off for the voltmeter. And then it's used to measure voltage. And you'll have a lab experiment talking about how ammeters and voltmeters work. The next property we want to talk about is resistance. Resistance can be thought of as the electrical equivalent of friction, because basically what it does is it takes kinetic energy away from the electrons and converts it into heat. So it's very much like friction in that regard. And it's also a means in a circuit of taking energy out of the current and directing it towards another end. So resistors tend to be semiconductors, and that's why semiconductors are so valuable. Conductors allow basically unfettered movement of the electrons. Insulators block the movement of electrons. Semiconductors regulate the flow of electrons, allow you to control how much current goes where. And so they're very valuable. Silicon, which is a type of semiconductor, is a very valuable commodity. Most commercial resistors are made of carbon, which is also a semiconductor. And there is a very simple relationship between the voltage across 2 points in a circuit and the current between those 2 points in a circuit. And it's given by Ohm's law, that the voltage is equal to the current times the resistance. And so this can apply for one resistor. It can apply to a segment in a circuit that can have multiple resistors. It can apply to the circuit as a whole. So it's a very powerful and very useful law. And the unit of resistance is the ohm. And so you'll typically see ohms, the symbol for ohms is the capital of the Greek letter omega, which looks kind of like a horseshoe. And an ohm is 1 volt per ampere. Now, in order to determine the resistance of a resistor or a stretch of wire or something along those lines, you need to know the substance that's involved and the resistivity of that substance. So resistivity is a substance-specific property, kind of like density that we talked about at the very beginning of the semester. And it's a measure of how strongly the substance inhibits the movement of charge through it. Resistivity is constant at a constant temperature, but it does vary a little bit with temperature. And so we'll talk about that. The resistance is equal to the resistivity multiplied by the length of the resistor divided by the cross-sectional area. So the longer the resistor is, the more opportunity it has to take energy away from the electrons that move through it, and that increases the resistance. But the wider the resistor is, the more opportunity there is, or the opportunity exists for more electrons to pass through at the same time, and that decreases the resistance. So resistance varies directly with length and inversely with cross-sectional area. And there's a proportionality constant involved called the resistivity. Conductors tend to have very low resistivity in SI units on the order of 10 to the negative 8 ohm meters. Insulators have a resistivity on the order of 10 to the 13 ohm meters. So 21 orders of magnitude difference, which is very, very large. And so this table gives you an idea of what different resistivity values are. For metals, for conductors, it's on the order of 10 to the negative 8. Semiconductors have a pretty broad range. So carbon, which is used in standard resistors, has a resistivity on the order of 10 to the negative 5 ohm meters. Germanium is about 0.5 ohm meter, and silicon is about 1,000 ohm meters. Then you look at insulators, and they have much, much higher resistivity. So glass 10 to the 10th to 10 to the 14, rubber 10 to the 13, sulfur 10 to the 15, quartz 10 to the 16. So very, very high resistivities. And the second column is the temperature coefficient of resistivity, which we'll talk about in a second. You know, it's on the order of 1,000th or 0.1% per degree Celsius. Notice also that for conductors, the temperature coefficient is positive, which means the resistance increases with temperature. For semiconductors, the temperature coefficient is negative, which means the resistivity decreases with temperatures. So the basic equation involved for the temperature variation of resistance, and since resistance and resistivity are proportional to each other, the equations are essentially identical, but the resistivity at a given temperature is equal to the resistivity at a reference temperature, typically 20 degrees Celsius. And so the values in the table are given at 20 degrees Celsius, but it doesn't necessarily have to be that value. And then in brackets, you have 1 plus alpha, where alpha is the temperature coefficient of resistivity. In SI units, it's in inverse degrees Celsius. And you're multiplying alpha by the change in temperature in inverse degrees Celsius, or the resistance, or the difference in temperature between the temperature T you want to measure the resistivity at, and then again, the reference temperature T naught, usually 20 degrees Celsius. And again, like I said, for the table I showed, it's 20 degrees Celsius. And then the equation for resistance is basically the same, that they both vary proportionally. And then we get to electrical power. So like I said, resistors take kinetic energy and convert it into heat. Well, how much energy per unit time do they take out of the circuit. So energy per unit time is power. And in SI units, it's measured in watts. Electricity is really the one area of physics where the units we use in everyday life coincide with SI units. So we use current, we measure current in amperes, or an electrician will measure current in amperes, potential difference in volts, power in watts, just like we do in SI units. And so power is the amount of work done per unit time. And so you go through the math, and what you get is that the power is equal to the current going through a segment of circuit multiplied by the potential difference between the two ends of that segment of the circuit. And that tells you how much power is lost. And you can write that three ways, because again, from Ohm's law, delta V is equal to I times R. So the power is equal to I delta V, but if you substitute IR for delta V, you get I squared times R. And if you substitute delta V over R for I, you also get delta V squared divided by R. So you can write the power in three different ways. It's similar to the energy stored in a capacitor, that there are three equivalent ways of writing that equation, depending on which two variables you know. So electrical power is typically expressed in units of watts. Electrical energy, if you look at your electrical bill, and if you look at electrical units, typically they don't use joules, or an electrician wouldn't use joules, or in your electrical bill, you won't see the energy used in terms of joules. You'll see it expressed in terms of kilowatt hours. Well, a kilowatt is 1,000 watts, or 1,000 joules per second. And an hour is 3,600 seconds. So you multiply those numbers together, you get 3.6 million, or 3.6 times 10 to the 6 joules. So that's how much energy is in a kilowatt hour. And so if you look at an electrical bill and you see the electricity expressed in kilowatt hours, remember that 1 kilowatt is equivalent to 3.6 million joules. Now, we're going to spend the subsequent chapter talking about DC circuits in particular. Basically, everything we've covered up to this point applies to either type of circuit, but we're going to talk a little bit about AC circuits now, and then revisit the subject a little bit in chapter 29. So in an AC circuit, the current varies sinusoidally around 0, which means half the time it's positive, going in one direction, half the time it's negative or going in the opposite direction. So you can write I is equal to I max times the sine of omega t. And omega is the angular frequency in radians per second. So it's related, mathematically very similar to the angular velocity in radians per second that we talked about when we had circular motion or rotational motion in physics 1. But this is more mathematically, this is more of an abstraction, but it does work mathematically. That you have your maximum positive value when omega t is equal to 90 degrees or pi over 2 radians. And, it's 0 when omega t equals 0 when it equals pi. And it's -1 when omega t is equal to negative pi over 2. So I is varying sinusoidally. The voltage also varies sinusoidally. And if there are no capacitors or inductors in the circuit or in that segment of the circuit, it oscillates in sync with the current. But we'll talk more, that's circuits that have inductors and capacitors in AC are a subject we will get to in physics 3. So some of you, those of you who move on to physics 3 will have to wait a semester to see it. So ammeters and voltmeters that are set to measure AC currents usually don't measure the maximum value of the current. They measure what's called the RMS current or the RMS voltage. And we went through the derivation of this in a previous lecture. but RMS stands for the square root. So R is root, mean squared. So the square root of the mean of the square of the value. So basically, you take I squared, you find the mean value over the entire cycle, and then you take the square root of that mean value. And so you get a value, you'll get your current in amperes if you do that, and your voltage in volts. Now, if it was simply the mean value of I, well, I is positive half the time and negative half the time. So the mean value of I over a full cycle is going to be 0. That doesn't tell you anything. But the mean value of I squared, since I squared is always going to be positive, will tell you something. And so when you go through the integration to figure out the mean value of I squared and then take the square root of that mean value, you find that the RMS current is equal to the maximum current divided by the square root of 2. And going through the same process with voltage, the delta V RMS is equal to the maximum voltage, also divided by the square root of 2. And if you want the power across the circuit or across a segment of the circuit, it's equal to the RMS current multiplied by the RMS voltage. Equivalently, you can write that as the RMS current squared times R, or the RMS voltage squared divided by R. And so that's all we covered for chapter 25. So let's now move to chapter 26, which is DC circuits. So DC stands for direct current. So the current comes from a source of voltage or sources of voltage that are constant in magnitude and direction. So you have a steady current. It's not shifting direction, and its magnitude is not changing either. You have a steady output coming out. And that's a DC circuit. So you've already seen DC power supplies in the laboratory. So DC circuits supply in all sources of voltage are said to exert what's called an electromotive force. Basically, the potential difference is associated with an electric field that exerts a force on the electrons that makes them move. And you need to be careful with the terminology because electromotive force is actually a potential difference and not a force in the physical sense of the word. But if there is a potential difference, then there is an electric field. And if there is an electric field, then there is going to be a force that's exerted on the electrons. And so the electrons get repelled out of the negative end, and they move through this circuit. And if it's a DC circuit, they're going to move at an essentially constant rate. Now, resistors can be combined, much like capacitors, into either series circuits or parallel circuits, and also separate segments of the circuit can be in series or in parallel. So you might find one resistor in series with two resistors connected in parallel. So that's entirely possible. But you figure out the equivalent or the total resistance one segment at a time. And so in a series segment of a circuit, the same current is flowing through all the resistors. The total voltage between the beginning of the segment and the end of the segment is equal to the sum of the voltages across the individual resistors. And from that, you get the total resistance is equal to the sum of the individual resistances. So in a series circuit, the resistors add together, or a series segment of a circuit, the resistors add together. In a parallel circuit, the current branches off. So the total current feeding into that segment is equal to the sum of the currents in each branch. But the potential difference across each branch doesn't change. So it's similar to capacitors in parallel in that sense. The voltage doesn't change. However, when you do the math, you find that the resistors exhibit an inverse relationship, kind of like capacitors in series, not parallel. So resistors, when you're talking about resistors in parallel, 1 divided by the total resistance equals 1 over R1 plus 1 over R2 plus 1 over R3, for however many resistors you have. For 2 resistors, you can write the total resistance as being equal to the product of the resistance divided by the sum of the resistances. So, but that only works for 2 resistors. So it's kind of like capacitors in series in that sense. Next, we talked about Kirchhoff's rules. Now, Gustav Kirchhoff was a German scientist, working in the mid-1800s, and he came up with a basic set of laws that govern the current and voltage in complicated circuits. Now, the math here may seem a little bit complicated, although if you're an EE major, you may have already seen it. But the math may seem a little bit complicated, but you have to keep in mind that if you stick to the formalism, it'll make more complicated problems simpler. And plus, if you have multiple equations with multiple unknowns, you're probably going to use the computer to solve the problem anyway. There are definitely coding computer programs that available, and you can probably design one yourself that'll enable you to solve the Kirchhoff's rules for a complicated circuit. So there are 2 rules. The first of which is the simpler one, the junction rule. The sum of the currents entering a junction must equal the sum of the currents leaving a junction. So for n junctions in a circuit, there are n minus 1 independent equations. So, and so the examples we went over in class typically had 2 junctions. And so you apply the junction rule at each location, you get the same equation out. And basically, the total current coming into a junction is equal to the total current coming out of a junction. So if I1 is coming in and I2 and I3 are going out of a junction, then I1 equals I2 plus I3. So the junction rule is conceptually fairly simple. The loop rule is a bit more challenging because you need to keep sign conventions in mind. So the loop rule says that the sum of the voltage rises and voltage drops across the elements in a closed loop must equal 0. So what does that mean? Well, we're going to stick to 2 different things you can have in a circuit, a power source and a resistor. And the next thing you need to do is assign directions to your loops and assign directions to your currents. Now, if your current is actually going in the opposite direction to what you assigned it, you'll get a negative value for that current. And that's not necessarily a bad thing. I mean, that doesn't mean you got it wrong. It just means the current is going in a different direction to what you originally assigned. And as long as you've done the math right, that's okay. You're not going to lose credit for that. So the first step in applying these rules is to determine which directions are positive and which are negative. So it's arbitrary, but there are some basic rules that go to that. So you assign a direction to each current, you assign a direction to each loop. And again, if you do the math and it turns out that the current value, and you do the calculations correctly, and you get a value for one of your currents that's negative, that means it's actually going in the opposite direction to what you assigned it. And if it's positive, it means it's going in the same direction to what you assigned it. In general, the safe way to assign current directions, if there is a power source involved, is to draw the current arrow going out of the positive end of the power source or the EMF source and into the negative end. And the same applies for loops. You'll spare yourself some confusion if you draw the loops coming out of positive and into negative. It makes the math simpler. So what are the sign conventions for the loop rule? So we'll start with a voltage source or an EMF source. If the voltage loop points out of positive and into negative, then you count that as a voltage rise. So if your loop goes out of positive and into negative, you add that voltage. And if your loop goes into positive and out of negative, you subtract that voltage source. And so that's how that sign convention works. Now, across a resistor, if the you have to pay attention to the direction you assign the current as well. If the voltage loop and the current arrow are pointing in the same direction across that resistor, that's actually a voltage drop, and you subtract I times R. But if the voltage loop, for whatever reason, is going in the opposite direction of your current arrow, across that resistor, then that's a voltage rise, and so you add I times R to that. So those are the sign conventions, and we went through a couple of examples of that. And the last thing we talked about in chapter 26, and in fact, the last thing we talked about that solely concerns electricity and not magnetism, are RC circuits. And that's when a resistor and a capacitor are connected in series. And if you remember the laboratory experiment, we did connect a resistor with the capacitor, so you could see it charging and discharging. You were able to, you notice there was a finite measurable amount of time that it took to discharge. So how do you figure that out? Well, you figure that out using calculus, and you define a quantity called the time constant, where T is equal to R times C, the product of resistance and capacitance. So keep in mind, resistance and capacitance, those values are defined by how you define current, which we'll get to at the end of chapter 28. But the product is always going to be in seconds, so it doesn't matter how you define your current or the units of current. So keep that in mind. But the derivation involves calculus. In a DC circuit, you essentially have a steady source of voltage being equal to the voltage across the resistor, which is I times R, plus the voltage across the capacitor, which is Q divided by C. Now, the current, I, is equal to dQ over dt. That's the amount of charge passing through a point in the circuit is also equal to the amount of charge accumulating on the capacitor per unit time. And so I and dQ dt are the same thing. And once you have that, you have a differential equation you can solve for Q. And so we solve that differential equation for the charging capacitor. So Q, as a function of time, is equal to the maximum charge that can build up on a capacitor, which is equal to C times the voltage feeding into that capacitor, and the maximum voltage coming from the power supply. So again, basically the charge builds up until the voltage across the capacitor equals the voltage feeding into that part of the circuit. And so Q is equal to Q max times 1 minus e to the negative t over RC, or e to the negative t over tau. And for a discharging capacitor, it's a simpler function. Q is equal to Q max times e to the negative t over RC. So the maximum value of Q happens right at t equals 0 when you turn the current on, or when you connect the circuit, and then it decreases at an exponential, at a negative exponential rate from that point. In both cases, the current decreases exponentially. It has its maximum value, which is equal to the voltage feeding into the circuit divided by R at t equals 0, and then decays exponentially from there. So I is equal to I max times e to the negative t over RC, or e to the negative t over tau. So that is chapter 26. And then we got to magnetism. Now, magnetism, before we start talking about magnetism, it's important to review some mathematics. Magnetism and the calculus-based physics really can't be done without working with vector products. And so vector products were introduced in Physics 1 with rotational motion, but it's worth reviewing some of the basic properties. So the vector product is a way of multiplying two vectors together that gives you a vector, whereas the dot product, like when you're doing work, for example, the dot product results in a scalar. So you're multiplying two vectors together and getting a scalar. The vector product, you're multiplying two vectors together and getting a vector. It's also called the cross product. So let's let C equal A cross B. So the X component is equal to AYBZ minus AZBY. The Y component is equal to AZBX minus AXBZ. The Z component is equal to AXBY minus AYBX. And so you see it written in the unit vector notation. If you're familiar with three-dimensional determinants, you can write C as being the determinant of a three-dimensional matrix where the first row is I hat, J hat, K hat. The second row is AX, AY, AZ, and the third row is bx, by, bz. And sometimes that's easier to remember than the way it is written here. So some properties of cross products. The direction of a cross product is perpendicular to the direction of the vectors that make it up. So what you do is you point your finger in the right hand, point the fingers of your right hand in the direction of the first vector. You curl them in the direction of the second vector. Your thumb points in the direction of the cross product. And so we have a right-hand rule going back to physics 1 concerning torque, or the torque vector, or the angular momentum vector. So you curl your finger in the direction of the rotation, or the direction of the angular acceleration when you're talking about torque, or the angular velocity when you're talking about momentum. Then your thumb points in the direction of the torque vector or the angular momentum vector. So those vectors don't point in the direction of motion. They point in the direction of the axis of rotation. So that's an important thing to keep in mind. That comes into play here. So let's talk a little bit about what magnets are. They have some similarities, and magnetism has some similarities and some differences with electricity, although ultimately you'll see that they're very closely related. A magnet does not have an isolated north pole or south pole. So electricity, you can have an isolated positive charge or an isolated negative charge. With magnetism, that's not possible. If you have a north pole, you always have a south pole. Now, some advanced physics theories say that it's possible in a collision with sufficiently high energy to separate a magnetic north from a magnetic south pole, but that has yet to be observed in an experiment or in nature. And so certainly for our purposes, magnetic monopoles don't exist, or you're not going to need to be concerned with one existing. One thing they have in common, magnetism has in common with electricity, is that like poles repel. So you put two north poles near each other, they will repel. You put two south poles near each other, they will repel. You put a north pole near a south pole, they'll attract. So it's a similar property to electrical charges in that sense. The magnetic field vector can be represented using field lines, similar to how electric field vectors can be made. The catch is when magnetic field lines point out of the North Pole and into the South Pole, the catch is with magnetism, there's always going to be a North Pole and a South Pole. So magnetic field lines kind of look like the experiment in the lab where you have the positive electrical charge and the negative electrical point charge. The magnetic field lines tend to look very similar to that, where they circle around from one to the other. Magnetism is another example of a field force. So it doesn't require contact for the force to exist. Magnetic fields exert a force on moving electric charges. So that's an important difference with electricity, that electrical forces or electric fields exert forces on electrical charges whether they're moving or not. Magnetic fields require movement. So that's one important difference between electric fields and magnetic fields. And what we'll see in the next chapter is that it takes moving electrical charges to create a magnetic field. Stationary electrical charges will not do that, but moving electrical charges will. So why is magnetism generally associated with attraction? Well, go think about what we talked about in the beginning of chapter 21 with electricity, with induced charges, that if you have an otherwise neutral object, but the electrons can move in it, and you put a positively charged object near it, well, that's going to attract some of the electrons. And so you have a negative side and a positive side in what was otherwise a neutrally charged object. So the negatively charged side is facing the positively charged object. There's going to be attraction. And if you put a negatively charged object near the neutrally charged object where the electrons can move, the electrons are going to be repelled, leaving a positive side near the negatively charged object. And again, you get attraction. Something similar works with magnetism, that certain metals, iron especially, have rotating electrons that are basically susceptible to a magnetic field. And if you put a magnetic field near these rotating electrons, they will orient themselves so that they create a magnetic field that points in the same direction. And what that means is that if you've got a magnet south-north here, the piece of iron will be aligned the same way. So you have south here and north here. So you have the north pole of the first one of the magnet near the south pole of the now polarized iron. They're going to attract. And so if you have if you have an electromagnetic needle, it'll pick up anything that around it that has iron for that reason. And similarly, if you've got a refrigerator magnet and you've got a stainless steel refrigerator, the stainless steel is mostly iron. So you put that magnet on the refrigerator, you're going to create a magnetic field within the stainless steel that lines itself up with the magnetic field due to the magnet, or due to the permanent magnet, and you wind up having attraction. And we'll talk a little bit about why that, the physics of that in more detail later this chapter, and we'll continue with that in the next chapter. So the most obvious magnet that we interact with on a daily basis is our own planet. The Earth has an iron core, and as a result, there's a magnetic field. So there are electrons moving within that the iron core, and that creates a magnetic field. And so the compass always points north because the horizontal component of the Earth's magnetic field is northward. There's a vertical component pointing up near the southern southern hemisphere and down into a point near the northern hemisphere. So the vertical component of the magnetic field, or the Z component of the magnetic field, is up in the southern hemisphere and down in the northern hemisphere. For the most part, the horizontal component is always going to be north, unless you're closer to the geographic poles than you are, than to the magnetic pole. But one thing to keep in mind, the Earth's magnetic south pole is near its geographic north pole, that the compass is pointing in the direction, is pointing north, which is in the direction of the magnetic field. And remember, magnetic fields point out of north poles and into south poles. So it's a little bit counterintuitive. So you'll need to be careful with that. But the Earth's magnetic north pole is near its geographic south pole, and the Earth's magnetic south pole is near its geographic north pole. The magnitude of the Earth's magnetic field varies from 2.5 times 10 to the negative 5 to 6.5 times 10 to the negative 5 Tesla, where a Tesla is the unit of magnetic field strength in SI units. And it's named for Nikolai Tesla, who was a Serbian immigrant who came to this country. He had a laboratory right here in Suffolk County on Long Island. His biggest contribution was as an electrical engineer. He, more than anybody else, is responsible for the electrical grid as we know it. And when we get to chapter 29, we'll talk about the physical principles that he used to determine, to make our modern electrical grid possible. So now we'll start to get quantitative. The magnetic force acting on a current is, so you have a current or a wire of length L and a current I flowing through it. The magnetic force is equal to I, the current, times the cross product of L and B, where L is, the magnitude of L is the length of the wire, and the direction of L is the direction of the current, again, from positive to negative. So basic properties of cross products, the force vector is perpendicular to both the wire and to the magnetic field. The magnitude of the force is equal to B times I times L times the sine of theta, where theta is the angle between the two vectors in the cross product. And so that's a general property of all cross products as far as figuring out the magnitude. If the current or magnetic field is not uniform, you multiply I by the differential length or element of length dl cross b, and then do the integration. So you evaluate the cross product first and then do the integration. And we'll see something like that comes into play when you're figuring out the magnetic field due to a current. So our first right-hand rule. You point your finger in the direction of the current, you curl your fingers in the direction of the magnetic field, your thumb will point in the direction of the force that the magnetic field exerts on the wire. And the more generalized version of this is the force of a charge moving in a magnetic field. So the vector form of that is F is equal to Q times the cross product of V and B. So the magnitude of F is the magnitude of Q times VB times the sine of theta, where again, theta is the angle between the velocity vector and the magnetic field vector. But in the vector form, there are no absolute value signs around Q. Its sign actually matters. So for positive charges, you use the same right-hand rule I just showed you. You point your fingers in the direction of V, curl them in the direction of B, the thumb points in the direction of F. If the charge is negative, you have two options. You can use the right-hand rule, but because it's a negative charge, the force points in the opposite direction of your thumb. Or you can use your left hand instead. Point your fingers in the direction of V, curl them in the direction of B, and your thumb points in the direction of your left thumb points in the direction of the force. Either way will work depending on which one you're more comfortable with. Cyclotrons are an important part of modern physics. When you think of the Large Hadron Collider at CERN, or the big accelerator at Fermilab, or the RIC right here in Brookhaven, you're talking about a large circular track on which charged objects are accelerated through a magnetic field. So how does that work? So going back to physics 1, we talked about an example of motion where the force acting on the object is always perpendicular to the object's motion. And that happens when there's when the object is moving in a circle. So there's always a force pulling it into the center of the circle, so acting perpendicularly to the object's motion. And so if you fire a charged object into a magnetic field, it's going to move in either a circular or a spiral motion, depending on whether it starts out perpendicularly to the, its initial V is perpendicular to the magnetic field, or whether there's a component that's parallel, in which case it will move in a spiral motion rather than a circular motion. But the radius of curvature is equal to mv divided by qb, where q is the magnitude of the charge, m is the mass, v is the magnitude of the velocity, and b is the magnitude of the magnetic field. And so a charged object that moves into a magnetic field will rotate in a circular path with that radius. And the cyclotron frequency, of the amount of the radians per second that the charged object passes through, is equal to QB over M. And so those are important. The original cyclotrons were actually handheld instruments, but to get the higher energy collisions, you need bigger bigger tracks than that. And that brings us to the basis of electric motors, the idea of a magnetic field acting on a loop of wire. So you have a loop of wire acting in the presence of a uniform magnetic field. What will happen is that there'll be a force in one direction on one side of the wire and a force in the opposite direction on the other side of the wire. So that leads to rotation. So if you set the wire on an axis, you can get it to move. And so this is the basis of electric motors. You expose a wire to a magnetic field, you put current through the wire will start to rotate. This is very similar physics, or only in sort of a reverse to AC generators, which we'll talk about in chapter 29. In an AC generator, you have a loop of wire inside a magnetic field. Instead of supplying a current to make the wire move, what you're doing is you're supplying motion to the wire. You're giving it the energy to rotate, and that creates a current. And we'll talk more about that when we get to chapter 29. So the wire experiences a torque that is equal to the current flowing through it, the area enclosed by the loop. So the geometry of the loop doesn't matter. It could be circular, square, rectangular, whatever you want it to be. But you have the area enclosed by the loop, you have the magnetic field in which it's rotating, and then times the sine of theta. Theta is the angle between the magnetic field vector and what's called the magnetic dipole moment vector. So the magnetic dipole moment has a magnitude of I times A, where A is the area enclosed by the loop. Its direction is determined by the direction of the current through the loop. And so you need a right-hand rule for that. So your fingers curl in the direction of I, your thumb points in the direction of the dipole moment. So electrons that are rotating, and this brings us back to what we were talking about in the beginning of the chapter with iron. The iron always has electrons rotating. If they're not in the presence of a magnet, the rotation is usually random. So you have a whole bunch of electrons and there's no pattern to their, that are circling around, but there's no rhyme or reason to it. But if you expose them to an electric field, suddenly their dipole moments will line up with B. And, because of the torque that's put on them. And so the force, the magnetic force will act to minimize the potential energy. And the potential energy of a magnetic dipole and a magnetic field, whether it's isolated electrons rotating or whether it's a loop of wire with a bunch of electrons moving, it's the same physics, that the potential energy in that loop of wire is equal to negative mu dot B, where mu, again, is the dipole moment, and B is the magnetic field vector. And so that's equal to negative I times A times B times the cosine of theta, where theta is the angle that B makes with the dipole moment vector. So it's the same theta that we have from the slide before, where you're figuring out the torque, that it's the sine of theta. So the force is going to act to minimize the potential energy, and potential energy is minimized when the dipole moment lines up with the magnetic field vector. So if you expose a piece of iron to a magnetic field, instead of the random orientation of the dipole moments, they will start to line up with the magnetic field vector. And what we'll see in the next chapter is that they wind up magnifying the magnetic field significantly as a result. But we'll talk about that a little bit more next time. So that's everything we covered from these 3 chapters. So if you have any questions before the exam, do not hesitate to email me. And otherwise, good luck with your study, and I will see you and talk to you soon.